Okay, good morning, everyone. So we want to continue our lesson about combinatorics that we started with the product rule. Okay, so mainly I want to write some questions for you, give you a little bit of time to think about that, and then we can discuss it together and solve the problem. Okay, so there is one problem that you see on this screen now. So a set is given to you containing elements A, B, C up to H, and then I want you to use the product rule to answer the following questions. Of course, the first part, how many subsets does A have? Probably you already know the answer, but I want you to think about it and try to write it in a way that is appropriate to using the product rule. So I want actually you to be able to prove that formula in the first place, because if you understand what's behind that reasoning that which gives rise to the formula 2 to the power of n, where n is the cardinality of the set, where this formula is coming from using the product rule, then you can immediately answer the next three questions, next three items in this question. Okay, so when you are busy writing this and trying to solve the question, I will try to find more interesting questions and add. So if you are finished with this one, you can start the other one. So what I'm trying to say, even if you are lazy to write all the details on the paper, don't be lazy to go through it in your brain. Yes. So what I mean, it means that if you want to use the product rule or the generalized product rule, you need to define a task for you first, so that this task can be broken down into a number of stages, and then see how many possibilities are there for each stage. And if the number of possibilities for a later stage is independent from how we have done all the previous stages. So even if you're lazy to write all these details on the paper, please try to review these things in your mind, because it would be crucial to understanding and using the chain rule effectively. The product rule effectively. Okay, so I will pause the video here, but in the meantime, I will start adding some more questions below that. Okay, so if you don't mind, let me take these two for the next page so that we have enough room. Just momentarily put them here. Okay, so for the first one, in principle, you have a task because you want to see how many subsets are there for A. So if I write a subset of A, say, for example, A, F, and H, this is my choice, for example, I just did it randomly. So it's not that random. So I was actually thinking about which elements I want to choose and which elements I don't want to choose, yes? So that is the idea. So if I want to answer this, so I would say this is 1, 2, 3, 4, 5, 6, 7, 8. Writing a subset of a set A is a task which can be broken down into eight stages. What can I call them? For example, the stage 1, I can say that I want to decide about A. So if this A is going to be in my subset or it is not going to be there. Yes. And then the second task would be decide about the situation of B. Do I want to put B in my subset that I am writing, or I want to exclude it? And the same scenario for C, and continue until H. So this is the way that you need to think about it. Otherwise, you always need to use your memory to be able to solve some examples that you have already seen, and you can compare them easily. So I don't want you to be bounded by those things. I want you to be flexible and try to solve harder problems, okay? So this is the way that I think. I want to write a subset. This subset is an 8-stage task, yes? The task, it is an 8-stage tasks. So the first stage is decision about A, which can be done in two different ways. What are those different ways? Either I decide for A to be in my subset, or I decide that A shouldn't be in my subset. There are two possibilities for A when I want to decide. Okay, so the first stage, decision about A, can be done in two different ways. Now assume that the first stage is done. So it means that either I have chosen to put A or exclude A. Now I go to the second stage, which is the decision, making a decision for the situation of B. Again, the same scenario happens. I have two options available for B. Either I choose B or not choose B. And this number 2 that I just want to write now is independent of how I have done the first stage, yes? This number 2 is independent if I have chosen A in the first stage or I have excluded A. So this is why this 2 is completely independent of how this is done. And then I go to the next stage. The next stage, I need to decide about C, okay? So for C, I have two choices available. I want to put 2, but I need to be careful. Is this number 2 independent of the ways that I have done stages 1 and 2? The answer is yes. So this 2 independent of how I have done the first stage and how I have done the second stage can be done in 2 stages. So everything goes on until the very last one. So because you can convince yourself that this is always the case, that each 2 is independent of the previous numbers. So you can use the product rule, and as you expected, so the answer is 2 to the power 8. By the way, that is enough. But if you want, you can also write 256. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's correct. Okay. But now, can you tell me what would be the answer of the second part? And I want to listen. What is your reasoning about that?
I would say it's 2 to the power 7.
Exactly. So for the same reason, yes. Can you just say why, for example? How did you think?
Because there's only one choice for A, but 2 for all the others.
Yes, exactly. So here it means that we have to write a subset containing A. So it means that there are no 2 options for first element. There is only 1 option. But after that, everything comes in 2 options. Yes. So this becomes 2 to the power 7, and then this becomes 128. Okay. Anyone else for part C?
It would also be 2 to the power 7 for a...
Yeah, exactly. But this time again, A has only 1 option available. Yes. But the reason that we put it 1, because we want to exclude it. We want certainly exclude A. So there is no 2 options for A. There is only 1 option for A. So this is 1, and then again 2 up to 2. So the answer is 2 to the power of 7, which is 128. So out of these 256 subsets in total, 128 of them contain A, and 128 of them don't contain A. Okay, and I think now you understand what's going on for the last one. Anyone else can answer this question?
2 to the power 3.
2 to the power of 3. 1, 2, 3, 4, 5. Yes. So how do you think about the problem when you want to start deciding? Yes. So let me write this list here: A, B, C, D, E, F, G, and H. According to this, how many options are available for A?
0.
No, A.
Yeah, I mean just 1, sorry.
Just 1, yes. So it means that there is only 1 option available for A, because according to what is written in the problem, A has to be in my subset. So there are no 2 options available here. There is only 1 option available for A, and that means that is putting A in my subset. The same thing for B, I have to put this B there, so there is only one option. But for C, D, and G, again, the scenario is clear. I have to exclude them. So again, there are only one options available for these. But the rest of them have two options available. So 2 for E, 2 for H, 2 for F, and 2 for H. And as you mentioned, if I multiply all of them, but of course you need to be careful. Can I use product rule? Yeah, you need to check the independency. So I don't want to repeat them, so you know that this is correct. So the answer becomes 8. Yes, is that clear?
Yes.
Good. Okay. Let me now bring one of these problems back there. Okay, so we now want to answer this question. Consider the set A. How many subsets of A are there so that 4 is the smallest? Let me write again, smallest element. Okay. I don't know. Do you have any idea how to solve this?
Yes. You look at each number and then see if that number has to have a certain state. So like 1, for instance, it has to be excluded, or else 4 won't be the smallest element. And so that means that you exclude 1, 2, and 3. And then you have to include 4.
Exactly. But others we have two options available, yes? So exactly. So if I want to write all of them in this list, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. First of all, when you say that 4 should be the smallest, implicitly it means that 4 has to be chosen in my subset. Otherwise, how 4 can be the smallest? So first of all, I understand that for 4, I have only one options available, and I have to include it. But if none of them should be in my subset, because otherwise 4 will not be the minimum. Yes. So this means that this should be 1, 1, and 1. So excluded, this is included. Yes, but from 5 onwards, I have only two options. I have two options, yes? So 2, 2, 2, 2, 2, and 2. So if I count them 1, 2, 3, 4, 5, 6, and I have to multiply all of them, yes? Because I hope that you can convince yourself that it's applicable here. So it is, how many of them are there? 1, 2, 3, 4, 5, 6. So 2 to power 6, which is 64. Any questions here? So I think that the next example would be now very clear, yes? So what I'm trying to teach you is to try to understand. So because if you do not have any strategy, just randomly want to multiply or add or something, it will not work, especially when the sum rule comes into game as well, okay? So you need to really understand what's going on. Okay, I think now the problem here is clear, yes? Consider the set A, the same set. In how many subsets of A is the smallest element 4 and the largest 8? Yes? So this becomes again clear, yes? So I have to decide about the situation of these elements. Okay, so when I say that 4 is the smallest, it means that 4 has to be in my set. So this means that for 4, I have only one option. This should be included. Okay, and then 8 is supposed to be the largest one. So there is only one option for this because this also has to be included. And then because 4 is supposed to be the smallest, none of the previous numbers should appear in my subset. So this is 1, 1, 1. They have to be excluded. And then because 8 is supposed to be the largest, so this has to be excluded as well. Otherwise, 8 cannot be the largest one. But any other one has two options. So, oh, sorry, I have to write it 1 and 1. And then I would write excluded. But for 5, 6, and 7, I have two options available. So this means that I have to multiply all of these possibilities. So it becomes 2 to the power 8, 2 to the power 3, which is equal to 8. Is that understandable?
Yep.
Okay, so there is also a nice problem. Let me write it. I want to see how do you think about this. I will write it down and then pause the video and wait for you a little bit. How many natural numbers let me write it in this way. By how many natural numbers so translation is a little bit hard. So let me see. Consider 2,400. By how many natural numbers No, I think this is not a very good sentence, sorry. So let me write it in a simple way. Okay, how many factors, how many positive divisors or factors are there for 2,400? Okay. Of course, one way to do that is to write the numbers for which 2,400 is divisible by, and then count them. For example, it's clear that 2,400 is divisible by 1. So 1 is one of the divisors, 2 is one of the divisors, 3 is one of the divisors. But I want to find a way, a systematic way, so that how can I count the number of positive divisors? If I just say divisors, of course, you just count the positive ones and multiply by 2, because there are also negative ones involved. 2,400. 2,400 is divisible by 1, and of course, minus 1. 2,400 is divisible by 2, and of course, minus 2. So even if I don't put this adjective here, that is still a simple problem. But the strategy that you can cook up so that you can solve this problem, not only for 2,400, for any type of numbers, that's very interesting. So I want you to think a little bit about that and find the connection between this question and the product rule so that you can design a strategy or come up with a strategy so that you can solve all these problems, not just for 2,400, for any natural number. Okay, so I will pause the video a little bit and wait for you. Okay, so did you come up with a strategy here? Not yet. Okay. So you see that these are the nature of combinatorial problems. The statement of the problems are very simple, but coming up with a strategy, with an effective strategy, is not that easy at all. Okay, sometimes it could be quite hard actually. So let me just wait a little bit more. No clues? So let me first tell you what the problem. Yes, do you have any idea?
I mean, if you were to pick a number, if you were to pick a number as a divisor, it has to be smaller than the square root of 2,400, I think. So I don't know if that's useful in this case.
No, probably I don't see any other, because I cannot say that this is useful or not. If you think that's useful, you need to convince me as well. Okay, but that's not the way that I am thinking. Yes. So let me make the problem a little bit simple. Assume that it was not 24. It was not 2,400. It was just 24. Because for 24, we can just do it like this. So if I want to write for 24, I can write 1, 2, 3, 4, and then 6, 8, 12. Am I writing all of them? Yes, and then finally 24. Yes, these are the only ones that we have. 1, 2, 3, 4, 6, 8, 12, and 24. And if I count them, 1, 2, 3, 4, 5, 6, 7, 8. But because this number was small, it was immediately possible for me to list all of them and then answer this question. I want to see, how can I cook up these numbers? Do you have any idea?
Mr. Babak, couldn't you create a set for all the prime divisors and then create the cardinality of every subset of these prime factors?
There are some truth about this statement that the prime factors are of course important, but exactly
set by the list, because we want to have, for instance, if the number were to be...
No, which prime numbers are important? So I don't understand. So if you come to the idea of prime numbers, first of all, there are infinitely many prime numbers. Are all of them are relevant in this problem or not? So this is the first idea that comes to mind. And it shouldn't be hard to realize that, of course, I factor 24, yes? So 24 can be written as 2 to power 3 times 3, yes? This is the prime factorization of 24. So it means that the primes that are involved in 24 are 2 and 3. The power of 2 is at most 3. So is 3, the power of 3 is 1. But now let us look where this 1 comes from. The 1 can also be written as a product of these two primes. But if I want to produce 1, there is only one option for me, write 2 to power 0 and 3 to power 0. So even though we never write 1 in this fancy way, but you need to come up with a strategy in order to be able to solve the problem. Yes, let me, for example, look at 2. 2 has the same structure as well. 2 can be written as 2 to power 1 multiplied by 3 to power 0. And then, for example, what is 3? 3 is 2 to power 0 multiplied by 3 to power 1. So let me emphasize top here 1 as well. And then when I go to 4, what happens? 4 is 2 to power 2, but multiplied by 3 to power 0. And when I go to 6, 6 is 2 to power 1 times 3 to power 1. And then when I go to 8, 8 is 2 to power 3 times 3 to power 0. And 12 is 2 to power 2 times 3 to power 1. Yes?
Is the answer for the question 256?
I don't know exactly, but I want to hear your strategy rather than the final question answer. Okay, so 2 to power 3, and then I will have 3 to power 1. So you see that here that I was able to list all of them. So this is actually giving me a very nice strategy how to answer this question, because I myself tell to myself, I tell to myself that 24 is in this form. If you want to write a number so that 24 is divisible by that number, it means that number should also be factorized into these primes. So I mean, for example, why 24 is not divisible by 10? Because if you write 10, 10 is 2 to power 1 times 1. It is clear that when I divide 24 by 10, it means that I am dividing 2 to power 3, 3 to power 1 by 2 to power 1 times 1. Of course, I have enough powers of 2 so that this becomes 2 to power 2, but the problem is here. 3 over 5 is a fraction, and when there is a fraction left after division, it means that this number on top is not divisible by this number. So the reason that this number is not divisible by 10 can be viewed in this way, because in the factoring of 10, I have a prime factor which is not a prime factor of that one. Okay, so this is one reason that 24 is not divisible by 10. But of course, I can have another scenario. Yes, let me just open a little bit of a space here. So I can have another scenario. For example, I can have 72. So 72 is 2 to power 3 times 3 to power 2. It contains exactly the same prime numbers. But again, 24 is not divisible by 72, not because 72 contains another prime factor in its factorization, because one of them contains a higher exponent than I have it in 24. Yes. So if I want to divide 24 by 72, then 24 is 2 to power 3 times 3 to power 1. But when I divide it by 72, it becomes 2 to power 3, 3 to power 2. I have enough powers of 2 to be canceled out. I have more powers of 3 in 72 than powers of 3 in 24. So this is another reason that might give rise that 24 is not divisible by 72. So it might happen that I have the same prime factors in its factorizations, but some of them or all of them have higher exponents, or sometimes I might have numbers in which I have some other factor, prime factor, other than these factors that I have seen here. So I think now everything becomes clear that if I want to count the number of divisors of 24, so my task is to write, so let me write it in this way. What is my task? My task is to write a divisor of 24. This is my task. But this task can be broken down into two stages. One stage is choosing an appropriate exponent for this 2, which can be 0, 1, 2, at most 3. And the second stage is choosing an appropriate exponent for 3, which can be 0 or 1. So if I ask you how many divisors of 24 are there, you would say that for choosing an exponent for 2, I have 4 options available. 0, 1, 2, and 3, 4 options for this power. And for this, I have 2 options available, either 0 or 1. So in total, how many options are available? 4 times 2 means 8. And if you count them, 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 divisors. So first, let me know if you don't understand something. Do you understand everything for 24?
Yes.
Is that clear? Okay, so, and then I hope that you agree with me that this is a very nice strategy that I can tackle all of these problems, yes? So for 2400, there is no big difference. So for 2400, so 2400 can be written as 24 times 100. 24 can be factorized in this form, 2 to power 3 times 3 to power 1, yes? But 100 is 10 to power 2, 10 is 2 times 5, so it is 2 to power 2, 5 to power 2, yes? This is 100. But 2 to power 2, 2 to power 3 can be combined, so this becomes 2 to power 5 times 3 to power 1 times 5 to power 2. So let me write it here. So this is the factorization of, so let me make it nicer. So this is the factorization of 2400. Now the task, let me write this carefully. So what is my task here? The task is to write a positive divisor. Yes, this is my task. So this task can be broken down into 3 stages. So can you tell me, for example, what is a stage 1?
Select how many 2s we want.
Yes, selecting the number of 2s. Yes. And stage 2, for clear reason, is the selecting. Oops, today I'm a little bit confused. Selecting the number of 3s, and then stage 3, selecting the number of 5s. Okay. So anyway, I don't say that you have to. What you need to think, you see this problem, I just wanted to wait. The problem was not that hard. Understanding the problem was very easy. You really understand what the problem wants from you, but it was not easy probably if you haven't come up with any strategy to come up with a good strategy to solve the problem. Okay, so here I was able to understand what's going on. So I would say that how many options are available for the first stage, let me call it N1. I want to select some number of 2s here, but I know that how many options are available. If I don't want, I don't need to choose any 2s at all. So it means that the lowest number of 2s that I can choose is 0. I don't choose it at all. But there is a higher bound on the number of 2s that I can choose. I cannot choose 6 2s, yes, because I have only 5 of them. So it means that either I choose nothing or 1 or up to 5. So how many options are there? So the options are 6. But I choose one of them. Either I choose 0 to 1 to anyway. So I know I have done the first stage.
Mr. Bob,
yes?
Isn't
yes?
there 32?
Pardon?
Isn't there 32 options for selecting? Oh, no, nothing. No, wait.
No, I am just calculating the number of 2s that I can put there. 2 to power 5 is 32, but that's not the problem, yes? So N2, what is N2? N2 means that how many ways I can select a 3, yes? How many 3s I can select at most 1. But I can decide not to choose 3 at all or choose at most 1 3. So how many options are available when I come to stage 2? This is 2. For writing this 2, you have to be a little bit careful. Is this 2 that I am writing here is independent of the first stage, how the first stage is done? The answer is yes. It doesn't matter how many 2s I have chosen in the first stage. I have 2 options available for the number of choices that I can make for 3. Okay, and then when I go to the last one, and 3 is the number of ways that I can choose of 5. But because the exponent of 5 is 2, it means that I can choose not to choose 5 at all, or 1 5, or at most 2 5s. So there are 3 options available here for me. But again, you need to be a little bit careful. Is this number that I put here independent of how the first and second stages have been done? The answer is yes. It doesn't matter how many 2s I have chosen in the first one, how many 3s I have chosen from the first one. I have still 3 options available for the last step, meaning that I don't choose 5 at all. I choose 1 5, or I choose 2 5s. So there are 3 options available. So according to the product rule, this task can be accomplished in N1 times N2 times N3, which is 6 times 2 times 3, and that is 36. So if you want, for example, you can write a computer code or whatever to write all the divisors, and then you immediately see that the total number of them is 36. If I just ask you how many divisors are there for this number, you multiply this number by 2, because for every positive divisor, it corresponds a negative divisor as well. That's the opposite of that divisor, okay? But first of all, is there any question? Is that understandable for everyone? Okay, so this is one of those problems that I want you to understand, that it is very good to have a strategy when you want to use the product rule. Okay, so if you understood what's going on, I don't think it would be hard for you at all to answer the second part of the question. So for example, here 3 is also a divisor of 2400, yes? But 3 is not divisible by 12, okay? So for example, here 24 is also a divisor of 2400, but 24 is divisible by 12. Now in the second part of the question, I want to see out of these 36 divisors, how many of these 36 are themselves divisible by 12. Okay.
I think it should be 8.
Okay, so I don't know the answers, but I want you to have a strategy.
My strategy is that I limit the number of 2s and 3s and 5s I can pick
Yes.
by first factorizing 12 in the same way.
Yes, so that's a good strategy. So let me just write it down. So what you are saying for the second part, let me factor 12 out. So this becomes 2 to power 2 times 3. Okay, so this means that, for example, what Alex said is actually correct. So here, I will not have 6 options available. Again, this is more or less the same, but the task will change to this: to write a positive divisor, which is divisible. Let me write with a different color, which is divisible by 12. So this would be my task. So I have to change a little bit the task. But again, this task can still be broken into 3 stages. Yes, S1, S2, and S3 with the same way of writing, but this will change these options available for me, the number of options available. Yes. So now here, when I didn't have any limitations, I could choose up to 5 2s. But of course, it is clear that I cannot go up to 5 2s here, because if I go up to 5 2s, then I cannot lower it. I can go up to 5 2s, but I cannot choose 1 2. Yes,
my answer was wrong. It should be 12. Yeah. Because I
okay. So let us come to that. Okay, but the idea is clear. So the idea is that I want to have this divisible by this. So it means that there is a minimum value. There is a minimum number of 2s that I can choose. For example, I cannot decide to choose only 1 2, and for example 1 3. Of course, this is a divisor of 2400, but this is not divisible by 12 because 12 has one more 2, yes? And if I divide them, of course, 3 and 3 are canceled, but the answer becomes 1/2, which is not an integer, yes? So this means that, okay, so now, if you understand what, let me save something for myself. So how many options are available for N1 now? How many options are available for N2? And how many for N3 now? Yes, so just answer this one. Well, how many of them are there? So
4.
4. Let me see. Yes, we can have 2, 3, and 5. So I would say 3, not 4. Is that understandable? Because the minimum number of 2's that I can choose is 2. I cannot choose lower than 2. So I can choose this power to be 2 or 3 or, yes, you are right, 4. Thank you very much. 2, 3, 4, and 5. Thank you. So this is 4. How many are there for N2?
1.
So it has to, yes, it has to have, this is 1. And how many are there for 3?
Still 3.
It's still 3. Yes? So the answer to the second part is N1 times N2 times N3. And the answer is 4 times 1 times 3, which is 12. Yes? So these are the answers for this question. Is it clear for everyone?
Yes.
Okay. So in general, can you tell me, cook up a formula? This is a famous formula in number theory, by the way. So if I have this, let me just introduce it. This is optional here. So let me write optional. So the number of positive divisors of a natural number n is denoted by, this is the Greek letter tau n is denoted by tau n, okay? If you factorize n to prime numbers, so let us say that it is p1 to power alpha 1 times p2 to power alpha 2 times p3 to power alpha 3 up to p sub k to power alpha k. Assume that you have a natural number and then you factorize your natural number into prime numbers, you get some combination like that in which p1, p2 up to pk are distinct prime numbers, and alpha 1, alpha 2, alpha 3 up to alpha k are the natural numbers. Yes? If n is this, then can you tell me now, can you tell me what is the formula for tau of n?
A1 plus 1 times A2 plus 1 times
exactly.
A3
So that is alpha 1 plus 1 times alpha 2 plus 1 times alpha 3 plus 1 up to alpha k plus 1. So that is a nice formula, yes? So from now on, you have a formula for the number of positive divisors of a natural number. And this is also a strategy. So if I ask you this question, you can factorize it. But of course, in the exam, you're not allowed to use the formula. If I give this question in the exam, you need to just give me the reason why this formula works in the first place. But anyway, we have now a formula. If I want to calculate the number of positive divisors of a natural number, the first thing that I do, I factorize it and I read these numbers. I add 1 unit to each one of these numbers and then multiply them. Why I need add to 1 to it? Because when I have alpha 1, there is a possibility that I don't choose P1 at all. So 0, 1, 2, up to alpha 1, how many options are available is alpha 1 plus 1. These plus ones are coming from the fact that I can choose not to choose any one of these factors at all. Okay? So that's completely optional, so I don't need, I don't want you to know about that. Okay, before going to the next stage, so let me ask you this question. Let me give you a set. A, B, C, D, and E. Okay. I ask you a simple question. So if I ask you how many subsets are there, you can immediately answer. How many of them are there? Yes, 2 to the power 5, which is 32, okay? So there are 32 of them. But now let me ask you, how many of them do you think have even elements, even number of elements? And how many of them have odd number of elements? Of course, it is intuitively clear.
I mean, intuitively, it should be half, right?
It should be half, yes. But do you think this answer of half depends on the cardinality of the original set as well? So what I'm saying is that here I have odd number of elements to start with. So for example, let me tell you my question. My question is that if I write A and B, it's a subset of A. If I ask you how many elements are there, you would say 2. 2 is even. So this is a subset of this set containing an even number of elements. But for example, if I write C, A, and E, this is also a subset of my set, but it contains 3, an odd number of elements. So you know that in total there are 32 of them. And in principle, it's not hard, even though it's a little bit tedious. You can list all of them and start counting them. Okay? Count which ones, how many of them have even number of elements. Yes. And then count how many of them have odd number of elements. Do you think this would be 16, 16? Or it might happen that, I don't know, I have 18, 14. Of course, intuitively, you might say that this would be split into half. Let us see. But I just want you to understand, it might be not that trivial. Or, for example, is it trivial if the starting set has even numbers of elements? So assume that instead of starting with a set with 5 elements and ask this question, I had started with this set with 4 elements, and now I am asking you the same question. Of course, here the total number is 2 to the power 4, which is 16. And then again, my question, do you believe that 8 of them have even number of elements and 8 of them have odd number of elements? So do you think that answering to this question somehow depends to the cardinality of the original set? Or no, it is always half of them, it's always the case that half of them have even number of elements and half of them has odd number of elements. Okay. This is the problem that I want you to think about that. Okay. So you need to be able to convince me that for any set, this might happen that the number of odd subsets and the number of even subsets are the same. Okay, so but I want you to, because I want it, so intuitively it might be clear, but I want you to put this in a firm ground and to be able to defend your arguments about that. Okay, so it is not, I wouldn't say it is very trivial, it needs thinking, but yes, the answer is correct. You are right. In both cases, half of them contains even number of elements and half of them contains odd number of elements when you do this subset. But is it a priori clear why this should be the case? Okay, so I will end this meeting here. I just keep this, I will answer this question and next time, but I want you to, in the meanwhile, to think about this, because again, in the book there are not many exercises that you can solve. I mean, still I am teaching those pages from the previous sessions. I'm just giving you more examples so that you are more comfortable with using the product rule and things like that. Okay, so that would be a good idea if you think about this problem and try to find an argument so that you can defend this idea that yes, independent of the initial number of elements, is it odd number of elements or is it even number of elements, the number of subsets containing even number of elements is equal to the number of subsets containing odd number of elements. Okay, so let me stop this video here.